now that we went through the parts of the hypothesis test, the possible outcomes, the types of errors, and how to develop the null and alternative hypothesis, we will do some examples on full hypothesis testing. And for reference, in the introductory statistics textbook, this is section 9.5, additional information and full hypothesis test examples. And again, in the Intro to Statistics Corequisite book by Lumen, we are still in Module 9 for hypothesis testing with one sample. So first, before you start a hypothesis test, you need to know, or you have to decide on the significance level alpha. If alpha is not given, then the standard would be to use alpha equal to 5%. You want to decide on the type of your test. Is it a left tail, a right tail, or a two-tail test? And this is determined by the inequality you are claiming, and that inequality is embedded in the alternative hypothesis. So the alternative hypothesis is the key to conducting the appropriate test. The alternative hypothesis will never have the equal sign. The equal sign is part of the null hypothesis. If the alternative hypothesis is a claim that your population parameter is less than the one stated in the null hypothesis, then this is a left tail test. If the alternative hypothesis claims that the true population is greater than, the true population parameter is greater than the one stated in the null hypothesis, then this is a right tail test. And if your alternate hypothesis states that the population parameter is not equal to the one stated in the null hypothesis, then this is a two-tail test. So the p-value will be the area in the left tail, the right tail, or split between the two tails, depending on the type of test that you are conducting. And you want to be critical of your p-value in a real statistical analysis. You want to be very critical of your p-value. If your p-value is really smaller or larger than alpha, then you have sufficient evidence. But if, let's say, alpha is 5% and you are rejecting the null hypothesis because your p-value is 4%, here I think maybe that should be a 0.04, or you don't reject it because now it is 5.6%, then you want to maybe conduct more studies in real applications. So it will be very tricky if your p-value is very close to your level of significance, because then you may not have really strong evidence to be very confident that you are answering this correctly. So one important thing is that you have to sketch the graph when you are solving a problem or thinking of a research that you are doing. And sketching the graph is extremely important for you to have a visualization of what exactly it is that you are trying to show or trying to find. So let's try to practice a little bit. The graph on the left that has the left tail shaded will be a left tail test. That says, notice here that the variable is the sample mean. So my null hypothesis will be that the population mean is equal to 5. Also, it could be that it is greater than or equal to 5. And then my alternative hypothesis will be the drawing from this sketch. So my alternative hypothesis here will be that mu is less than 5. For the next one, the one in the middle, notice here that p hat is the proportion of the sample. So this is the distribution of a sample proportion. I see that the right tail is shaded. This is a right tail test. The alternative hypothesis will be that the population parameter, p or pi, is greater than 0.2, and your null hypothesis will be either that p or pi is equal to 0.2 or that p or pi is less than or equal to 0.2. Remember that the equal has to be part of the null hypothesis, otherwise you cannot have a distribution to sketch, because for your distribution you need the mean. The next test here on the right has both tails shaded. The type of test is a two-tailed test. And that says that the alternative hypothesis, and again my variable here sketched on this graph is the sample mean. So the alternative hypothesis will be that the true population mean is not equal to 50, but the null hypothesis will be that the mean is equal to 50. One other thing that you want to pay attention to is that if your test is a one-tail test, either left or right, then the shaded area must be equal to the p-value. But if your test is a two-tail test, then the p-value will have to be split within the two areas. So we have a symmetry here in all the distributions that we use, normal or t-distribution, when we are doing a hypothesis test. The symmetry implies that the tail on the left and the tail on the right in a two-tail test will be identical to each other in terms of area. So your p-value will be 2 times the area of each tail, and therefore the area of each tail will equal to 1/2 of the p-value. So let's try to do an example. Jeffrey, as an 8-year-old, established a mean time of 16.43 seconds for swimming the 25-yard freestyle with a standard deviation of 0.8 seconds. His dad, Frank, thought that Jeffrey could swim the 25-yard freestyle faster using goggles. Frank bought Jeffrey a new pair of expensive goggles and timed Jeffrey for 15 25-yard freestyle swims. For the 15 swims, Jeffrey's mean time was 16 seconds. Frank thought that the goggles helped Jeffrey to swim faster than 16.43 seconds. Conduct a hypothesis test using a preset alpha level of significance equal to 0.05 and assume that the swim times for the 25-yard freestyle are normally distributed. So the distribution, that is the hypothetical distribution, says that the mean time that Jeffrey will swim the 25-yard will equal to 16.43. And Frank wants to find out if, in fact, he can be faster, which means that he will have a mean of less than 16.43. And the evidence that he has collected is a sample of 15 swims with goggles and a sample mean of 16 seconds. And also we do know the standard deviation of the population because they have calculated the mean of all the previous swim times and the standard deviation of all the previous swim times to be 0.8 seconds. Alpha is already predetermined. It is 0.05. And the random variable we are checking will be the mean swim time for 25 yards. And the units for that will be in seconds, but also it will be the mean of a sample of size 15. And for this distribution, we want to find the distribution of the sample mean for samples of size 15 And remember that the distribution coming from an approximately normal population of data with a known standard deviation will be X bar follows the normal distribution with a mean equal to the mean of the population, 16.43, and the standard deviation will be the standard deviation of the population, 0.8, divided by the square root of n, and n is 15. So remember that if you are using art of stat, you need to find a decimal approximation of this value. And when I did it in my calculator, it comes out to be 0.2065591118. I'm going to try to enter as much of that as I can in art of stat, which is the technology that I will use to answer this question. So my first step here would be to actually sketch the normal distribution of the sample means. So this, let me actually try to make it a little wider since I have the space. There we go. So the variable here is the sample mean. Time to swim a 25-yard lap in seconds. And this is the distribution of the sample mean. So every tick mark, the mean will be 16.43, but every tick mark will be 0.206 or 207 or 0.21. Whatever you want this to look like. But again, I will use art of stat to give me those values so that I don't have to calculate them by hand. So I went here in art of stat, I set the mean to be 16.43. I set the standard deviation to be the decimal approximation I found in my calculator. And before I start doing the test here, I want to just copy this graph and the values here in the bottom for the sample mean. So I did 15.81, 16.02, 16.22, etc. here in my notes. And my test statistic is actually a z-score. And that z-score is the z-score of the sample mean of 16 that I found. So I need to find somewhere the value of z equal to 16 minus the mean divided by the standard deviation of 0.8 divided by the square root of 15. So I need to find this value for the test statistic. And it comes out to be negative because it is the sample mean of 16 is less than the theoretical mean of 16.43. So negative 2.0817. And that is, if I go here in the art of stat and I say that I want to find the value of x to be 16 and I asked it to show me the z-score, the z-score will be the negative 2.081729. It gives it to me with a little more accuracy here than what I wrote. And remember that your alternative hypothesis is that the mean will be less than 16.43. So when you find this 16 and you see again that it is a little more than 2 standard deviations below the mean, that's what the z-score indicates. The z-score is the number of standard deviations we will be below the mean or above the mean. Then we are looking for a lower tail test. So we are looking for the p-value to be the area here below that z-score or the particular sample mean that we have. So what is the p-value? The p-value per the ArtofStat is 0.0187 or 1.87%. So let's write that. This is our p-value, 0.0187. If we have different technology like Excel or a calculator, we can find it with more accuracy. It is 0.0186836. But it rounds to 0.0187. So did we have an unusual outcome? And the answer is that yes, this p-value of 1.87% is actually smaller than the level of significance alpha, which was 5%. And that means that if the theoretical mean is 16.43, then the sample we got of 15 swim times is actually unlikely to come from this population. It has almost 2% chances of coming from this distribution versus the 98% of all the other potential times that could come from this distribution. So since my p-value indicates a rare event, then I will have to reject the null hypothesis. That means I have enough evidence to support the alternative hypothesis. So at the 5% level of significance, we can conclude that Jeffrey swims faster using the new goggles. Or we have sample evidence to show that Jeffrey's mean is below 16.43 seconds when swimming with the goggles. Remember to always start your conclusion with the significance level and to always refer to the alternative hypothesis. So to say that you either have enough sufficient evidence to support the alternative hypothesis or you don't have enough evidence to support the alternative hypothesis. Also remember that an unusual event, which is a small p-value, is the evidence to support your alternative hypothesis claim. Now, there are two other ways we could answer or solve a hypothesis test. One of them is to use the z-score, the test statistic, and the other is to use a confidence interval, which we have seen before. So when we use the test statistic, we, instead of comparing the p-value to alpha, we will compare the test statistic, the z-score, to the z of alpha or the z of alpha halves, that, depending on the test, that represents the actual direction of the test we need. So for this example, we are looking for a left tail test. So when we are looking for a left tail test that has a mean of 0, z-score, right, and a standard deviation of 1, and we are looking for the unusual outcomes or the rare outcomes to be the outcomes on the left 5%. So we need this z of alpha so that this area here is 5%. The probability is 5%. Then any z-score that falls into that area of unusual outcomes will be a z-score that indicates a rare or unusual event. An event that consists or provides enough evidence that the sample data can support the alternative hypothesis. So for this one, we will want to go to the standard normal distribution that has a mean of 0 and a standard deviation of 1, and we want to find the percentile or quantile that gives us in the lower tail a probability of 5%. And this will be our z-score. So the z-score, it's called the critical value, is z equals to negative 1.645. So in this case, the critical value will be negative 1.645. This is the z-score that cuts the values of standard scores into the rare events. The rare standard scores will be below negative 1.645, or in the ones that do not alarm us, do not indicate something unusual. So these will be the usual events. Anything greater than negative 1.645 is close enough to the mean or to not be able to support our alternative hypothesis, but anything that is unusual or rare will support the alternative hypothesis. We found a z-score that was negative 2.0817. This is in the critical area, so the decision will be, because we have a test statistic in the critical area, then we have enough evidence to reject the null hypothesis. So our decision will be to reject the null hypothesis, and our conclusion will be that at the 5% level of significance, the sample data provides sufficient evidence to support the claim that Jeffrey's 25-yard swim times are less than 16.43 seconds when using the goggles. I forgot to stress in my conclusion that we are referring to the mean swim time and not to any particular single swim time. So I corrected this up here in this conclusion earlier. I said that we are talking about Jeffrey's 25-yard mean swim times, and also I made sure that I added it here. So again, remember that in your conclusion, the variable of investigation is the mean swim time, and that's why we have the distribution of the sample mean being a normal distribution or approximately normal. So there is another way again to solve or to answer a hypothesis test, and that is to actually construct a confidence interval centered around your sample mean, and then see if that confidence interval actually includes the theoretical mean of 16.43 seconds. Now here is a trick, however. In order for you to capture a 5% area in each of the two tails, because the confidence interval is a two-tailed test. If you want to create a confidence interval here, you need to make sure that you have 5% on the left and also 5% on the right. So that will mean for you that you will want to construct a confidence interval with a confidence level of 90%. And that will ensure that you will actually find the correct z-score, the correct critical value on the left and on the right of your center. And your center here, remember, will be the sample mean and not the theoretical mean. You want to see if the theoretical mean will be within the confidence interval. So if I go in Art of Stat and I try to find again percentile and quantile, I want this time for the confidence interval the mean to be a 16, and I want the standard deviation to be the standard deviation of the distribution of the sample mean. And if you remember, that was 0.20, 6559, 1118. And I want a two-tailed test, and I want the central probability here to be 90. So I will end up, if this was a standard distribution, so let's go back to a 0 and a 1 for the standard deviation. If this was a standard normal distribution, I would correctly have found the z-scores of negative 1.645 and positive 1.645. And you remember that this was the critical value. But when I am using actual values, then these are translated to values of the variable being the sample mean. And the sample mean of a sample size of 15 swim times. We are looking for a two-tailed test. The central probability will be 90. This will give us 5% in the left tail, which is what we want, and 5% in the right tail, which is again what we want. And the interval of times will be from 15.66 seconds to 16.34 seconds. So the confidence interval here will be from 15.66 seconds to 16.34 seconds. And I see here that the theoretical mean is not in the interval. So the confidence interval tells me that I am 90% confident that the true population mean would be between 15.66 and 16.34, and it will not be equal to 16.43. Therefore, I have enough evidence to reject the null hypothesis. And again, my conclusion will be the same. At the 5% level of significance, the sample data provides sufficient evidence to support the claim that Jeffrey's 25-yard mean swim time is less than 16.43 seconds when Jeffrey swims with goggles. So regardless of which method you use to solve a hypothesis test, the conclusion should always be the same. So you should always, your decision and your conclusion. So whether you choose the p-value, whether you choose the critical value, or whether you choose to solve it with a confidence interval, all methods should provide the same answer.